Hello friends, I welcome you all to this class. This is linear algebra class, and today we'll be looking at this theorem, Cayley Hamilton Theorem. And this theorem states that every square matrix satisfies its own characteristic equation. Every square matrix satisfies its own characteristic equation. This is what the theorem states. So the matrix must be a square matrix, and it must be an n by n matrix. That's a square matrix. And the theorem says that as far as the matrix is a square matrix, it will satisfy its own characteristic equation. So before we what we need to know here is what is the meaning of characteristic equation. We need to know the meaning of characteristic equation. Before we know that, let's know the meaning of a characteristic polynomial of a particular square matrix. So the characteristic polynomial of a particular square matrix A is given by P of lambda. This lambda is just a scalar. So P of lambda, which equals determinant of A minus lambda I, and is equal to a sub 0 plus a sub 1 lambda plus a sub 2 lambda squared into a sub n lambda raised to power n. So this is the characteristic polynomial of any given square matrix. So to find the characteristic polynomial of any given square matrix, you need to compute the determinants of a minus lambda I. I is the n by n identity matrix. So now what is this characteristic equation? This characteristic equation, you can easily get it by setting the characteristic polynomial to be equal to 0. So when the characteristic polynomial is equal to 0, you will get the characteristic equation. So which means you have to compute determinant of a minus lambda I and equate it to 0. So this will give you the characteristic equation. So then by the Cayley Hamilton Theorem, this square matrix A will satisfy this characteristic equation. So if you plug in A for lambda, that is in this equation, anywhere you see lambda, you put matrix A. And since you are putting the matrix A anywhere you see lambda, then this constant, you are going to multiply the constant by what? Identity matrix, n by n identity matrix. Because for you to you cannot add this constant alone with all these because all these ones will be a matrix. The constant times a matrix will give you another matrix. So constant a sub 2 times this matrix A square give another matrix. So if you are adding a matrix and a particular, you can't add a matrix and a particular constant. So that's why we are multiplying the constant by what? Identity matrix, so that you can add it. So when this equation is satisfied by the Cayley Hamilton theorem, this equation will be satisfied as far as you plug in the matrix A into the characteristic equation. So with that, let's quickly verify the Cayley Hamilton theorem of this very matrix A. This is a square matrix and it's 2 by 2 square matrix. So to do that, what we are going to do is quickly we are going to get the characteristic equation of this particular matrix and then plug in the matrix into the characteristic equation. So let's get the characteristic equation of this. So we are going to compute determinant of A minus lambda I and set it to be equal to 0. So this implies determinant of what is matrix A, that's 1 2 negative 1 3 minus lambda multiplied by identity matrix. Because matrix A is 2 by 2 matrix, then this identity matrix will be also 2 by 2 identity matrix. Then you set the determinant to be equal to 0. So then this implies determinant of, we have 1, 2, negative 1, 3, then minus lambda multiplied by 1 lambda, lambda multiplied by 0, 0, lambda multiplied by 0, 0, lambda multiplied by 1 lambda, determinant equals 0. And this implies, so determinant of, let's subtract 2 or 1 minus lambda, I have 1 minus lambda, 2 minus 0, 2, negative 1 minus 0, negative 1, 3 minus lambda, 3 minus lambda, determinant equals 0. So this implies, this is a 2 by 2 matrix. Now I want to get the determinant of it. So we multiply the principal diagonal, that is this multiplied by this 1 minus lambda and 3 minus lambda. Then you subtract the product of the other diagonal. So negative 1 multiplied by 2 will give you what? Negative 2. You are going to do, so you'll be doing negative, negative. So which will be positive, have positive 2. Then you set it to be 0. So quickly you can open the brackets. 1 multiplied by 3, 3. 1 multiplied by negative lambda, negative lambda. Negative lambda multiplied by 3, negative 3 lambda. Negative lambda multiplied by negative lambda, positive lambda squared. Then plus 2 equal to 0. Quickly, this simply implies we have lambda. Let's write lambda squared first. Lambda squared, negative lambda, negative 3 lambda will give you negative 4 lambda. Then 3 plus 2 we have 5, positive 5, which equals to, we have equal to 0. So this is the characteristic equation, right? Then let's plug in the matrix into this this characteristic equation and see whether we are going to get the same thing equal to 0, whether we are going to get equal to 0. So P of A, so we'll plug in this matrix A there. So you are going to have A squared, anywhere you see lambda you put A there, negative 4A. Then 5 is a constant, so you are going to multiply it by what? Identity matrix, since the constant 5i. So we want to check whether this will give us 0. Let's check. This will be, A is 1, negative 1, 2, 3 squared minus 4, 1, 2, negative 1, 3 plus 5i. The identity matrix will be 2 by 2 because our matrix A is 2 by 2. So this will be, let's quickly expand this. This will be 1, negative 1, 2, 3. Because we're having squared, right? 1, 2, negative 1, 3 minus 4 into 1, 2, negative 1, 3 plus, okay, no space. So this we have 5, 1, 0, 0, 1. So this will be equal to, let's multiply. You use the row to multiply the column. 1 multiplied by 1, 1. 2 multiplied by negative 1 will be what? Negative 2. So you add both of them, you are going to get what? You are going to get negative 1. So next, you use this first row to multiply the second column. 1 multiplied by 2, you get 2. 2 multiplied by 3, you get what? 6. You add both of them, you are going to get what? 8. Then to use this to multiply this last row to multiply the first column. Negative 1 multiplied by 1, negative 1. 3 multiplied by negative 1, we have negative 3. So if you add, you are going to get negative 4. Then negative 1, this last row, this last row multiply this, the other column. Negative 1 multiplied by 2, we have what? Negative 2. 3 multiplied by 3, we have 9. So if you add, you are going to get what? You are going to get positive 7. So we have minus 4 multiplied by 1. 4 multiplied by 1 is what? 4. 4 multiplied by 2 is 4 multiplied by negative 1, negative 4. 4 multiplied by 3, we have what? 12. Plus 5 multiplied by 1, 5. 5 multiplied by 0, 0. 5 multiplied by 0, 0. 5 multiplied by 1, 5. So this will be equal to, so what I want to do now is let's subtract this one, then later I'll add it to the other one. So negative 1, negative 4, because we have minus here, we are going to have negative 5. 8 minus 8, 0. Then for this one, we have negative here. Negative will be what? Positive. Plus 4, you have what? Plus negative 4, you have what? 0. Then 7 minus 12, you have what? Negative 5. Then plus the last matrix, 5, 0, 0, 5. So by the time you add, you are going to get what? You are going to get 0, 0, 0, 0. So this has shown that this matrix actually satisfies what? It satisfies this characteristic equation. So Cayley Hamilton theorem is verified.